everyone, welcome to the new session of the chapter Haloalkanes and Haloarenes. Today we are going to start a new topic, methods of preparation of haloalkanes and haloarenes. This is a very important topic. In this we will see different methods of preparation of haloalkanes and haloarenes. First we will focus on the preparation of haloalkanes. Okay, now when we go with the preparation of haloalkanes, we can prepare them from hydrocarbons, we can prepare them from alcohols. Okay, we have different methods of preparation. We will see each method in detail. In that, we will first focus on preparation of haloalkanes from hydrocarbons. You people know what are hydrocarbons? Compounds which are exclusively made up of carbon and hydrogen are called hydrocarbons. In grade 11, you had a very big chapter of hydrocarbons where you have studied in detail about alkanes, alkenes, alkynes, their methods of preparation and their properties. So you people have a very basic idea on hydrocarbons, which are mainly classified into alkanes, alkenes and alkynes. Now you can prepare haloalkanes from both alkanes, alkenes and alkynes, but the method, the way in which we prepare them is completely different. Okay, because you people know alkanes don't have unsaturation, so alkanes from alkanes there will be a different method of preparation. Alkenes and alkanes they have unsaturation, so there we will use a different method of preparation. Now, as you people have been studying from grade 10, very well, you people know that alkanes undergo only substitution reactions. Okay, you people know that alkanes undergo which reactions? People know alkanes undergo which type of reactions? Alkanes undergo substitution reactions. Alkanes undergo substitution reactions because alkanes are less reactive. Alkanes are less reactive. You people know alkanes are called what? Paraffins also. So alkanes are less reactive. So alkanes preferably undergo substitution reactions. What are substitution reactions? Substitution reactions are those reactions in which one atom or a group of atoms is substituted by other type of atoms. Okay, if one type or one atom or a group of atoms are substituted by a different type of atoms. Okay, for example, if you have methane, in methane you will remove one hydrogen and put one chlorine. Okay, so you will be substituting one atom or group of atoms with other group of atoms. Okay, this is already studied in grade 10, so you people know alkanes undergo which reaction? Substitution reaction. Now, when we go further into substitution reactions, especially in this chapter, we will see that from alkanes we prepare what? From alkanes we prepare haloalkanes, and what is the process we are using here? Substitution reaction. So alkanes undergo substitution reactions, giving which compounds for us? Haloalkanes. Now when I say alkanes undergo substitution reaction to give haloalkane, again in substitution reaction there is a special type of substitution reaction here taking place, which is your free radical substitution reaction. Okay, you people know what are free radicals. Okay, you have any particular atom, any particular atom. For example, I take X atom. On this, if you have a single electron. Okay, on this, if you have a single electron. Okay, single electron which is not involved in any bond. Okay, you have this single electron which is not involved in any bond, and it is there just like that on the atom. It is like free to react. Okay, this particular electron which is there on atom X, it is free to react. Now if you want to understand the difference, if it has two electrons, then I call this as what? Lone pair. This is not free radical. I have an atom X with a lone pair of electrons. Okay, now free radical is, when do I call it a free radical? When I have the atom X, on that I have a single electron which is ready to bond with any other free radical. Okay, now so this species is free radical. Now because and it will be a very unstable species. Free radical has a single electron and it will be very unstable species. It will be very unstable species. Now because it is very unstable species, free radical always wants to react and become stable. So free radical is highly unstable. When I say something is highly unstable, then I can write it as very reactive. Okay, when something is unstable, it wants to become stable, so it prefers to react. So it is highly reactive. Now if you see, I clearly told alkanes undergo substitution reactions. To give haloalkanes, alkanes specially undergo free radical substitution reactions, and I told you what are free radicals also. Clear? Now if you see here, from alkanes we are going to prepare haloalkanes by free radical halogenation, which are substitution reactions. Free radical chlorination or bromination of alkanes. Now here what I am going to do, I clearly told you we are doing free radical substitution reactions. Okay, we are substituting some atom in alkanes by halogen. We are substituting some atom in alkanes by halogen. Means what? For example, let me take an example here. For example, you take your methane. Okay, for example, you take your methane. Now methane, I have to do substitution reaction of methane, or I have to do substitution reaction. Means what? I have to substitute halogen by some other atom. Because I want haloalkane, I will substitute hydrogen with chlorine. I will substitute hydrogen with which atom? Chlorine. Okay, chlorine or bromine, whichever you want. Either you can do chlorination or bromination. If you are getting it out, ma'am, why are you talking only about chlorination or bromination? Why not fluorination and iodination? We will also discuss fluorination and iodination in a separate part after this. Okay, it has some different scenarios, so we'll see it there. Okay, now one hydrogen should go from here and one chlorine should substitute it. Now because halogen is substituting hydrogen, we call this process as halogenation. We call this process as halogenation. You people know what are halogens? Main halogens we study: fluorine, chlorine, bromine, iodine. So I am doing substitution with which? With an halogen. So I am calling it as free radical halogenation reaction, which is a type of substitution reaction. Now ma'am, show us how it is free radical. That we will do. We will do the mechanism of this reaction, where you people will clearly understand what are free radical halogenation reactions. Now, as I told you, alkanes don't prefer to react. I have to perform this reaction in the presence of sunlight or UV rays. I can do this reaction in the presence of sunlight or UV rays. Or else the chlorination and bromination process will not happen, because alkanes are less reactive. Now, one hydrogen will be substituted by one chlorine. Will the reaction stop here? Definitely no. We are doing in presence of sunlight. That too, it is going by a mechanism of free radical halogenation. Free radical reactions are basically uncontrollable. Why are they uncontrollable? Because free radicals are very unstable. They always want to react. Okay, so they are very unstable species. So whichever possibility is there, they'll keep on going on reacting. So because it is such uncontrollable process, because it is uncontrollable, I clearly told it is very difficult for us to separate the products. This part I'll go later. First let me write the reaction. Now this process will not stop here. This process will not stop here. So what will I do here? Again it will react with chlorine in the presence of sunlight. Here if you see, one hydrogen has been substituted with chlorine. So I am, okay, so minus HCl. Okay, from here hydrogen will be removed, and from here chlorine will be removed, and it is minus HCl. Now this reaction will not stop here. I have what? I have my chloromethane. Let me write the names for this, IUPAC names. Methane. This is my chloromethane. Yes. Now it will not stop even here, because I still have hydrogens. One hydrogen can be substituted by chlorine again. So I will get CH2Cl2 by removal of HCl. What is the name of this? Dichloromethane. What is the name of this? It is your dichloromethane. This reaction will not stop even here. It will go further. Now Cl2 in the presence of sunlight, one more hydrogen, so I get CHCl3 minus HCl. Still I have a hydrogen which can be substituted by chlorine. So this reaction will still go further. Cl2 in the presence of sunlight minus HCl, and I will get my CCl4, and the reaction will stop here. Now, if you see this process of halogenation, obviously a substitution reaction which is taking place by free radical mechanism, that mechanism we will see after this. But if you can understand here, did it stop at a monochloro derivative? See here, if you see, free radical chlorination or bromination of alkanes gives a mixture of isomeric mono or polyhaloalkanes. Did you get a mono isomeric? We will see. Did I get only a monohaloalkane? No. I got a monohaloalkane, I got a dihaloalkane, I got a polyhaloalkane. So the reaction will give you multiple products. So I can say the reaction will give a mixture of isomeric mono or polyhaloalkanes which are difficult to separate. Now in the reaction mixture, I have methane, I have chloromethane, I have dichloromethane, I have trichloromethane. I didn't write the names here. Okay, I have trichloromethane, which is very famously called as your chloroform. Then it is your, okay, what this is your tetrachloromethane. This is your tetrachloromethane. So I got different products in the reaction mixture, but usually we don't want all the products. We don't want all the products to come. Might be I don't need dichloromethane. Might be I don't need tetrachloromethane. If you specifically want one type of product, then this reaction will give you multiple products. Now you have to again invest lot of time and invest lot of amount in separating your desired product from this mixture of products. That is the reason in this reaction, this process is usually not preferred, because it gives a mixture of products. Again, it is very tedious for us to isolate our required product. That is the reason the required yield is very low. Yield is very low. It is not a selective process. You get a mixture of process. Yield wise, we don't prefer it. In terms of selective product also, we don't prefer it. Okay, we don't prefer it that much still. Okay, if you feel I can isolate, then it is fine. You can go for it. Okay, like this I get a mixture of mono or polyhaloalkanes which are difficult to separate, and the yield of this reaction is very low. So this is a basic understanding of what kind of reactions alkenes undergo to give your haloalkanes. Okay, basically it is free radical halogenation reaction. Now I have given you a general basic understanding here. Now let us see the mechanism of this. Okay, when I told you methane gives chloromethane, dichloromethane, trichloromethane and tetrachloromethane, it is very important for us to understand how are they formed. And the mechanism is very important, in which you have 3 steps: your chain initiation, chain propagation and chain termination. So we are going to see the free radical halogenation mechanism using the halogenation of methane. Because if you go for already for methane only, you get many products, and to understand it is very confusing. That is the reason if I go for higher members like propane and butane, it becomes still more tougher for us to understand the process of free radical halogenation. So let us try to understand it by using methane. Then when we start writing the reactions for propane or butane, it will become very easy for you to understand how are you getting the products. Okay, so this is the brief introduction. Now let us see how to write a mechanism for the halogenation of methane through free radical substitution mechanism. Okay, so next let us do that. Let us see the mechanism for the free radical substitution of methane. Okay, we are doing halogenation here, so let us see the mechanism. Okay, if we see this was our reaction. Okay, we started with chlorination of methane in the presence of sunlight, and we have seen the reaction didn't stop at CHCCl, but it went till CCl4. Now if you see the chain initiation reaction, so it is a chain reaction, because I told you free radicals are highly unstable. They won't stop at particular point and the reaction continue in the form of a chain. So for any process there should be an initiation. So how will this process get initiated? Basically is the chain initiation reaction. And our chain initiation reaction is, we have a Cl2. Yes, sorry. Okay, let me write here: in the presence of Cl2, in the presence of Cl2, in the presence of Cl2, in the presence of Cl2. You can do even this for bromination also. Now if you see here, Cl, now because it is happening in the presence of sunlight, now sunlight will trigger the breaking of the bond. Here the bonds breaks in such a way that it breaks in homolytic fashion. When it breaks in a homolytic fashion, what will happen? The bond breaks symmetrically. The bond breaks symmetrically. Homolytic fusion will give you the symmetrical breaking of the bond. So one electron, 2 electrons are involved in this bond. So one electron will go to this chlorine and one electron will go to this chlorine, giving us what? 2 free radicals of chlorine. Okay, this is how my reaction gets initiated, where Cl2 breaks down in the presence of sunlight, giving Cl dot, which are my chlorine free radicals. Now this will initiate the process. Okay, it is initiating the process. Okay, after chain initiation we have chain propagation. Now this Cl2 will go and react with methane. Okay, now the chain will propagate. Now if I take my methane, plus Cl dot. Now if you see here, now CH4 structure, if I want to show you, like see here, this is the structure of my methane. Now what will happen is, because the free radical is highly reactive, now the free radical will go and substitute one of the hydrogen here. Chlorine comparatively is more powerful than hydrogen. That is the reason it becomes very easy for chlorine to go and substitute hydrogen from here. So what it will happen here? Here again homolytic fusion of this bond will happen. So here how you can see this, I am showing you. Okay, how you can see this? You can see you have a free radical here. Okay, and hydrogen gets separated as a free radical. And hydrogen gets separated as a free radical. Now this CH3 dot free radical will be here. Okay, this CH3 dot free radical will be there. Now plus HCl. Okay, this hydrogen H dot free radical will react with Cl dot free radical, forming HCl, and my methyl free radical will remain as it is. Now, I told you it is an uncontrollable step, so it keeps on reacting. It is not that I have only one chlorine molecule in the process. I have millions of chlorine molecules in the process. So this CH3 dot will react with 1 mole Cl2 molecule which is there in the reaction mixture. Again, you people can understand this bond will break. It will give Cl dot. This Cl dot will react with CH3 dot, giving what? CH3Cl plus Cl dot. Clear? This bond breaks. Now you will get Cl dot. If you want, I will show you. Here I will get Cl dot and Cl dot. This Cl dot reacts with CH3 methyl free radical, giving CH3Cl. Okay, and my chlorine free radical. Now this is my halogenation reaction. Okay, this is the reaction till here. But because it is an uncontrollable, okay, this is an uncontrollable process, will I get only this product? No. Apart from chloromethane, I'll get many other products. Now, how will the other product form? We will see. So the chain will keep on propagating. How does the chain, okay, how does the chain propagate? Let us see. Now I got my chloromethane. Okay, now I got my chloromethane CH3Cl. Okay, I have my chlorine free radical. Okay, now this chlorine free radical will go and do what? It will react with this. Okay, it will react with this and give what? CH2Cl free radical. Okay, CH2Cl free radical plus HCl. Okay, CH2Cl free radical plus HCl. If you want, nothing will happen here. I will show you. Okay, CH2, this is one bond, no, CH3Cl, I am writing like this. Okay, so this bond will break. So I will get one hydrogen free radical here. It will react with chlorine free radical, giving HCl and CH2Cl dot. Now for every step I will not show the bond breaking because it is understood now. Okay, now this see here the bond broke. I got H free radical, hydrogen free radical plus chlorine free radical formed HCl, and this is my CH2Cl free radical dot. Because it is a radical now, will it stop here? No. Now this CH2Cl, okay, now this CH2Cl will react with one more chlorine molecule which is there in the reaction mixture, because there are many, now how far the reaction will proceed? Now if you are asking, ma'am, how far will the reaction proceed? Is there any possibility the reaction will stop here? Is there any possibility the reaction will stop at CH2Cl2? Now that will depend on how much chlorine is there for availability of chlorine. If more chlorine is available, it will go till here. If less chlorine is available, might be it will stop till here. So what is your deciding factor here? The amount of chlorine available for the free radicals. So based on that, the reaction will stop where? That will be decided. Now I am imagining enough amount of chlorine in the reaction mixture, so we will do it till the end. Now this bond will break. Okay, now this bond will break here. So now what will I get here? I will get my CH2. Okay, so this bond will break. So here what I will get? Cl dot. Okay, now I will get my CH2Cl2. Okay, I will get my CH2Cl2 plus from here I have my Cl free radical. Okay, from here I have my Cl free radical. Now this will again not keep, but is the reaction stopping here? No, the reaction is not stopping there. So my dichloromethane will again react with a chlorine free radical. Here I have a chlorine free radical. It will react with the chlorine free radical. Now when it reacts with chlorine free radical, what is going to happen here? It will form. Okay, now I told you very previously also, now this bond will break. This bond will break as I showed here. Okay, now this bond will break and I will get what here? Okay, here I will get HCl. Okay, here I will get HCl because from here one hydrogen will break and will react with this. So here what will I get here? Here I will get my CHCl2. Okay, here I will get my CHCl2 free radical. Okay, here I will get my CHCl2 free radical because from here one hydrogen will go and react with chlorine free radical, giving HCl, CHCl2 free radical. Now what will happen? This is free radical again. Now will this keep quiet? It will search for chlorine molecule in the reaction mixture. Now this will react with the chlorine. Okay, this will react here. Okay, this will react here with the chlorine molecule in the reaction mixture. Now as usual, again this bond will break. It can see Cl dot here. It can see Cl dot here. So what it will do now? Okay, what it can do now? It will take one Cl dot from here and become CHCl3 plus Cl dot. The other Cl dot will remain here. See here, I got my dichloromethane, I got my tetrachloromethane. Now again, if there is still enough amount of chlorine, this CHCl3 will react with, okay, chlorine. Okay, here it has chlorine free radical, here already it has chlorine. See, whatever possibility is there, it will go and react. No, this chlorine free radical will not keep quiet. It will be like, why don't I react with this CHCl3? Now what will happen? Again the same thing I have shown you. It will try to take one hydrogen from here. It will try to take from hydrogen from here and become HCl and become HCl. So what is the remaining part here? You will get CCl3 free radical. Okay, you will get CCl3 free radical. Now will this CCl3 radical keep quiet? Now no, it will search again for a chlorine molecule. Now CCl3 free radical plus chlorine molecule. Again you know the story. This will become Cl dot and this will become Cl dot. This Cl dot will go and react with this and will give what? CCl4 plus Cl dot. Okay, so this is how your chain propagation takes place, and you got your dichloromethane, trichloromethane and tetrachloromethane. Now if you are like, will this never end? Okay, it will end. When it will end? See, as long as the radicals are free, they'll try to interfere with something. See, here the radical was free, it was interfering with dichloromethane. Here the radical was free, it was interfering with my tetrachloromethane. Here my radical is free. Now, okay, now the thing is, as long as the radicals are free, the reaction will keep on propagating. As long as the radicals are free in the reaction mixture, the reaction will keep on propagating. So, for it to happen, now when two radicals come towards each other, when two radicals react with each other, a new bond is formed, then the termination takes place, because the radicals will become stable now. Okay, when the radical finds other similar kind of very stable radical or a stable radical, it will form a perfect molecule. Then the radical becomes stable, so then it will keep quiet. Okay, now if Cl dot radical, okay, finds other Cl dot radical, it will form a stable chlorine molecule. Fair enough. Okay, now here if you see the chain termination here, now if you can take this also, now methyl free radical, if it finds proper ClC radical, we have seen CHCl is formed. This is also possible. Now here the thing is, because it is methane, I can't get other step, but if it is any other alkane, you can even get this step. R dot plus R dot will give RR. Okay, R dot plus R dot will give RR. Now in case of methane, it is not possible, because methane has only one carbon. Okay, because methane has only one carbon. But if you go for the other alkanes, you can even see this kind of thing. Okay, where the two methyl radicals will combine, okay, combine to give CH3. Okay, that is also possible. Here it is not possible because my methyl free radical doesn't have other methyl free radical. That is the reason I can't talk about this step. But if it is any other alkane, you can see this step also. If you do it with ethane, then you have every possibility. At the end, again you will get ethane, because methyl free radical can react with other methyl free radical. So in this case, if you see, this is the okay, this is a very these are the two main possibilities where you can see the reaction will go to a termination. Okay, now when the reaction goes to the termination, now there is no point that if all the free radicals have reacted and become stable, then obviously the reaction will terminate over there. Okay, so this is how my reaction initiates, my reaction propagates, and my reaction terminates. Okay, only thing is, everything is decided by the amount of chlorine which is present in the reaction mixture. Okay, so this is the mechanism of free radical halogenation reaction, which is your substitution reaction. As such, you should know the mechanism. You should know the mechanism because you should understand when we go further, why are we getting many products and when will the reaction stop. Okay, if it is stopping, why it is stopping. For that, I have taught you this. So whenever two free radicals come together, so here I have not, okay, here did I show you anywhere in chain propagation? If you see, did I show you anywhere two free radicals coming contact with each other? No. If that would have happened here, then I shouldn't have called it propagation. Okay, I am calling it propagation because a free radical is reacting with a molecule producing other free radicals, so it will continue. Free radical reacts with normal molecule, okay, giving other free radical, so the reaction will continue. When it will terminate, if a free radical finds any other free radical and forms a stable bond, then itself my chain reaction will terminate and there is no further reaction taking place. Okay, so this is how you need to understand the mechanism of free radical halogenation reaction, okay, of alkanes to give my haloalkanes. It is very much obvious, there is no selectivity here. You will get all the products and it is kind of uncontrollable reaction and the yield is very low. Now we have seen it for methane. We will see for we have seen for methane with respect to the mechanism. Now we will see it for butane. Okay, we'll see it for butane and propane. So that for that we'll not write a mechanism like this, but you should be able to know, if I have taken butane, what kind of products will I get? And if I'm getting different products, and you people know you will get a mixture of products. If I'm getting mixture of products, which will be major and which will be minor. Now how to decide which product will be major and which product will be minor, that we'll do by taking a very important example of butane. Even propane you can do. I'll show you with butane, you can try propane. Okay, so let us do that part now. We have seen halogenation of methane. Okay, now let us see halogenation of butane. The mechanism is same, it will happen through free radical substitution reaction. Now if you see here, if I take butane, okay, it will undergo halogenation. We are doing chlorination here in the presence of light or UV radiation. Okay, I should have written here heat. Okay, heat. Okay, in presence of heat, light, H nu is nothing but here. Okay, sunlight only, UV radiation also you can use, heat, light. Okay, chlorination will take place. Now if you see here, I can get two types of products here, 1 chlorobutane and 2 chlorobutane. Okay, 1 chlorobutane and 2 chlorobutane. Now if you see here, I have written 55% of 2 chlorobutane and 45% of 1 chlorobutane, which very clearly tells that this is my major product and this will be my minor product. Now if we try to understand why are we getting two different products, 45 is not so less. Okay, we are getting 1 chloro and 2 chlorobutane. Now if you see here, when I started the class, I gave you an introduction where I told there is every possibility we get isomeric haloalkanes. Am I right? I told they can be isomers. That is the reason it is very difficult to separate. I'll throw a little light on that concept now. If you see here, I have done chlorination of butane, and there is now if you see here, this is my primary carbon, this is my secondary carbon, this is my secondary carbon, and this is my primary carbon. If the chlorination is happening at the primary carbon, my product will be this. If the chlorination is happening at the secondary carbon, my product is this. Now if you see properly, the product which is major is formed by the chlorination of the secondary carbon. Now okay, that we'll see later, but if you see these two products, they are isomers of each other. To be more precise, they are positional isomers. So I can clearly say that these two are isomers. Now when I say these two are isomers, their physical properties are almost very closer. Okay, their physical properties, chemical properties are almost very closer. There might be a very slight difference in terms of boiling point, but it is very difficult to separate them because they almost have the same properties. So that is the reason it becomes for me, it is very difficult for me to separate these isomers, which I can say is one of the major drawback of this process, because they are isomers, almost same physical and chemical properties, little difference in the boiling point. Now if you want to do distillation also with that such minute difference in the boiling points, even using distillation it becomes very difficult for me to separate them, because if you see in grade 11 you would have studied separation techniques where you have studied distillation, and you people know that there should be minimum certain difference in boiling point, then only it is easy for me to separate the compounds. But that you don't see here because the difference in boiling points is very, very negligible. Okay, it is difficult to separate everything we understood. But why it is 1 chlorobutane and 2 chlorobutane? It is very obvious because we have two types of carbons here. The substitution will be of two types, so we are getting two different products. But how to understand this in terms of free radical mechanism? Okay, in terms of free radical mechanism, which will be major, which will be minor? Why can't I take this as major, that as minor? We will see. For that, okay, let me take two possibilities here, CH3, CH2, CH2, CH3. Okay, I can do the halogenation of this H nu in the presence of sunlight. Okay, I will do halogenation. There are two possibilities that can happen here when I do chlorination in the presence of sunlight. What are the two different possibilities? The first possibility is the hydrogen from primary, let me write, okay, the hydrogen from the primary carbon can undergo cleavage, okay, homolytic cleavage, giving me, okay, giving me hydrogen free radical. Now from here also you people know this Cl will break, giving Cl dot and Cl dot. Clear? Now this hydrogen will react with this Cl forming HCl. Now this chlorine will attack here, giving CH2Cl. Now if I write the product, what do I get? That is the reason I was explaining the mechanism using methane over there. So what will I get here? CH3, CH2, CH2. Now this has got cleaved, so this will be CH2 dot. Because this is CH2 dot, this Cl will come and attack here, it will become CH2Cl plus. Now this hydrogen will be a free radical, it will react with this chlorine free radical, giving me HCl. So what is the product I got here? The product I got here is 1-chloropropane. Okay, 1-chloropropane. That is fine. But what is the intermediate I am getting here? CH3, CH2, CH2. Now because this bond is breaking, what type of radical am I getting here? This is my radical, this is the intermediate radical I will be getting here, because here this bond is breaking, so I get CH2 dot. So this is my which type of radical I am getting as an intermediate in this reaction? This is my primary free radical. Okay, this is my primary free radical. In the same way I can do here with respect to my secondary carbon. Okay, if you see with respect to your secondary carbon, now this hydrogen will break. Okay, this hydrogen will break here. So I will get what? Okay, I will get what as a free radical? Now see here, this Cl2 bond will break. So I will get Cl dot here and Cl dot here. Okay, now this hydrogen will react, this hydrogen free radical will react with one Cl dot, giving HCl. Now I have one more chlorine free radical that will react with this CH dot. That will react with this CH dot. So what will be my intermediate here? Intermediate free radical CH3, CH2, CH dot, CH3. Now this is my free radical intermediate here. Now what type of free radical it is? It is your secondary free radical. Okay, it is your secondary free radical. So what will be the product here? Because the bond breaks here, so Cl will attack here. What will be the product here? CH3, CH2, CH, Cl, CH3. So here I got my 1-chloropropane. Okay, and here I got my 2-chloropropane. Now if I have to decide, which is more stable. Now you people know from grade 11 only that whichever reaction proceeds to a stable intermediate, that will be my major product. Now if you see the intermediates here I got a primary free radical. Now here I got a secondary free radical. Okay, now in whichever reaction the intermediate is stable, that will be my major reaction leading to the major product. Now if you see the stability of free radicals, okay, now if you see the stability of free radicals, I'll write here, if you see stability of free radicals. Okay, now if you see stability of free radicals here, tertiary free radical is more stable than secondary, and then it is your primary. Now why is secondary free radical more stable than secondary? Why is secondary more stable than primary? The major reason is your hyperconjugation, which you have studied in your grade 9 in your general organic chemistry. The more number of hyperconjugating structures the free radical forms, the more stable the intermediate will be. Now here tertiary has 9 tertiary will have, let us not go into the depth of hyperconjugation. Tertiary will have more number of hyperconjugating structures. If you want to know, it will have 9 hyperconjugating structures. Secondary will have 6 hyperconjugating structures. Primary will have 3 hyperconjugating structures. So we are not going into the detailing of the number of hyperconjugating structures, but for now understand that tertiary free radical is more stable than secondary is more stable than primary, based on the concept called hyperconjugation. The more number of hyperconjugating structures it has, the more number of structures it will form. Okay, for a brief understanding, okay, how can I decide how many hyperconjugating structures will be there? I'll tell you very briefly. CH3, CH2, CH2, CH2 dot. Okay, now you can see this is my free radical. Now alpha carbon of that you take. Okay, alpha carbon of that you take. How many hydrogens does this alpha carbon have? 2 hydrogens. So it will form 2 hyperconjugating structures. Now if you see secondary free radical CH3CH2, okay, CH dot CH3. Now this is my, okay, this is my radical. The carbons which are beside it, I call them as alpha carbons. The hydrogens attached to alpha carbon will be alpha hydrogens. So how many alpha hydrogens do I have here? 5 alpha hydrogens. So I will get 5 hyperconjugating structures. Here I will get 2 hyperconjugating structures. Okay, this is how, based on the, so this is not needed for us right now, but just for if you have a doubt like how can you decide the hyperconjugating, decide the stability of free radical, we decide it on the basis of your hyperconjugation. How many hyperconjugating structures you get, that is decided by the, okay, that is decided by the alpha hydrogens in that free radical. So here it is understood. So which is more stable? Secondary free radical is more stable due to more hyperconjugating structures. So this will be my major product. So this is how you decide the major product and minor product when we do the when we do the halogenation of any alkane. Okay, when you do the halogenation of any alkane. This is for your understanding how, why is tertiary more stable, then secondary, and then primary. The same logic you can apply even for your carbocation. Okay, the same logic applies for your carbocation. Okay, now hope you understood how to decide major and minor products when I am doing the free radical halogenation process. So this is how you decide based on the intermediate. Where the intermediate is more stable, that product will be, okay, the major product. Okay, now, okay, we got 1 chloropropane, we got 2 chloropropane. Is it that I get only 1 chloropropane and 2 chloropropane? Will the chain not propagate further? Okay, or if you are, okay, see, I got a free radical here, I got a free radical here. Is it compulsory that this free radical will react with Cl dot and give this structure only? No, there is every possibility. Now in propagation, anything can happen. This cannot stop here, this can go even further. As I showed you in methane, did it stop at CH2Cl2? No. Did it stop at CHCl3? No. Now there is no guarantee that the reaction stops here. It can go further also. But these are the major products we get. If you give more availability of chlorine, it is very much obvious that the reaction will not stop here. It will propagate further. But as for now, with the normal availability of chlorine we have, these two will be the major product which can be isolated properly. Clear? Yes. Okay, now you can try the same kind of reaction for propane too. Yes, propane you can take it as homework and you can write in the similar way. Okay, now here you have primary carbon and secondary carbon. So here also you get 2 kind of products. In that 2 kind of products, which will be major product and which will be your minor product. Okay, which will be your minor product. All that you can decide here. So here I have shown you regarding the hyperconjugation also, so that you understand the concept better. Okay. So let us now try to understand little more important concepts of the reactivity of halogens here. Okay, reactivity of alkanes you understood now. Whichever will give more stable free radical, that will give the more major product. That is fine. Regarding alkanes, we understood based on the intermediate we can decide major and minor. But what about the halogens? We are frequently talking about chlorination and bromination only. What about fluorination and iodination? Why are we not throwing much light on fluorination and iodination? We will understand what happens in those reactions and why are they not so considered and studied in detail as this. Everything we'll see, but hope you have understood this for now. Okay, let's do the next topic. Now, let us see the reactivity order of halogens towards free radical halogenation. Now, from this concept, many times questions keep coming asking for the reactivity order of halogens towards free radical halogenation, and the reasons are also very important because sometimes they might ask the reasons too. Now, if you see, we talk about fluorine, chlorine, bromine, iodine. Okay, the 4 halogens. Now, if you take the 4 halogens, fluorine, chlorine, bromine, and iodine, and talk about the reactivity order, the reactivity order goes like this. Fluorine being the most reactive towards free radical halogenation reactions, and iodine being the least reactive towards the halogenation reactions. Now, if you see the reasons for this, okay, let us first see the reason why fluorine is the most reactive. Fluorine see, usually we say that like it is a better reactive entity than all of these three, but fluorine is not only better than these three, but it is so highly reactive, very highly reactive entity. Okay, highly reactive for halogenation. Fluorine is highly reactive for halogenation. Now, if you go with the reason why it is very highly reactive towards halogenation, the reason is, if you see in fluorine, the bond length is very less. So here you have the electron cloud of fluorine. Here you have the electron cloud of this fluorine. Now the electron cloud of both the fluorine atoms keep on repelling each other. Okay, they keep on repelling each other. Now because they keep on repelling each other, okay, due to the small size of fluorine, the bond length is less, so the electron cloud of both the fluorine atoms keep repelling each other. Now when they keep repelling each other, this bond between fluorine atoms becomes weak. Okay, this bond when bond between fluorine atom becomes weak. Now when the bond is very weak, it is very easy for us to break the bond. So fluorine is highly reactive. This bond is weak due to what? Due to electron repulsions. Due to electron repulsions between the fluorine atoms, this bond is very weak, and that makes fluorine very highly reactive. Okay, and okay, very highly reactive. Now, okay, when we talk about chlorine and bromine, okay, when we talk about chlorine and bromine, so here if you will write this also, fluorine will break and form two fluorine radicals which are very highly reactive. Okay, and the fluorine radical is like, the fluorine radical is very unstable, so it becomes highly reactive entity. Now if you talk about chlorine and bromine, okay, in the presence of sunlight, they break into radicals. Okay, they break into radicals. Now if you compare both of them, bromine breaking down into bromine radicals is a pretty difficult process. Now if we go into the reason why it is a very difficult process when compared to chlorine getting broken down into chlorine free radicals, there is a reason. Because this fission of bromine, homolytic fission, if it is forming free radicals, what kind of fission is there here? Homolytic fission. Now if we talk about here, this homolytic fission requires lot of activation energy. Now if I talk about activation energy of the of breaking of chlorine into chlorine free radicals, with the bromine breaking down into bromine free radicals, this process needs 4 times more activation energy. This process needs 4 times more activation energy compared to the cleavage of chlorine molecule into chlorine free radicals. Because it needs 4 times more activation energy, now you can easily understand how difficult is it for this process to take place. That is the reason bromination, when you talk about halogenation, bromination is not that preferred, or bromination is not that quick when you compare to your chlorination process. Okay, so that is the reason. First comes here fluorine. Due to the electron repulsion, the bond becomes very weak and it is very highly reactive, very highly reactive compared to these three. Now when you come to chlorine, okay, next will be chlorine. Okay, next will be chlorine. Chlorine has not so high activation energy. Okay, but when you come to bromine, it has 4 times more activation energy when you compare the cleavage of chlorine into chlorine free radicals. Now when you come to iodine, okay, now when you come to iodine, iodine has a very important points to remember here. Okay, iodination we usually don't prefer because iodine is not that reactive. Now why is iodine not that reactive? Let us see the reasons. Now iodine is not that reactive because when iodine breaks down into iodine free radicals, okay, when iodine breaks down into iodine free radicals, now these free radicals, iodine free radicals, are compared to the other free radicals, they are comparatively stable. Okay, these iodine free radicals are comparatively stable. Now because the iodine free radicals are comparatively stable, okay, they become less reactive. Okay, now one more reason for being less reactive, is iodine free radicals, okay, are big in size. Okay, iodine free radicals are big in size. Okay, iodine free radicals are big in size. Okay, the first reason is when iodine molecule breaks down into iodine free radicals, these free radicals are comparatively stable, so they don't prefer to go into a chemical reaction. Now iodine free radicals are big in size. Okay, iodine free radicals are big in size, so they don't prefer to react much. Okay, if you go further into the reasons, when iodine performs this free radical halogenation reaction, what exactly happens is chain propagation. Okay, the chain propagation steps are highly endothermic. The chain propagation steps are highly endothermic. Now, when you go with the process, when you go with the mechanism of free radical substitution reactions, the first step, chain initiation, chain initiation, we need to give heat energy, we need to give light energy. So there it is clearly chain initiation irrespective of whatever halogen you take. You take fluorine, you take chlorine, you take bromine, you take iodine, irrespective of whichever process you take. Okay, chain initiation, you need to supply energy, so it will be what? Endothermic. It will be what? Endothermic. Okay, any halogen you take, chain initiation will always be endothermic. Now when you come to propagation step, this propagation step can be exothermic. This propagation step can be exothermic or endothermic. Propagation step can be exothermic or endothermic depending on the halogen you take. Now when you come to iodine, this chain propagation is highly endothermic. Now when you have to supply lot of energy for propagation, then it is very difficult. Okay, usually it can be endothermic. Now if you take the other halogens also, it is endothermic, but it is not that highly endothermic, is that the process is so difficult for it to take forward. But when you come to iodine, the chain propagation step is highly endothermic, so the reaction is very difficult to proceed further. So it becomes very less reactive. So these are the various reasons why iodine has very less reactivity towards the free radical halogenation reactions. Now, okay, we understood that chlorination and bromination we have seen in detail, along with the mechanisms, taking examples. We have seen chlorination and bromination. Now when we come to fluorination process, now when I talk about the process of fluorination, okay, let us see it. Okay, CH4 plus F2. Okay, now when this reaction takes place in the, okay, now if you see fluorination, for fluorination I need not give any sunlight also, because it is already very reactive. Fluorine is already very reactive. You need not supply any energy for it, it will automatically happen. So here what do you get here? Here you get your CH3 HF. Okay, now what is the problem with this reaction is, this reaction releases enormous amount of heat. Okay, this reaction releases enormous amount of heat. Now because this reaction is highly exothermic, okay, because this reaction is highly exothermic, it almost becomes what? Explosive reaction. Okay, it almost becomes an explosive reaction. Okay, so fluorination, because fluorine is very highly reactive, the reaction releases enormous amount of heat, making it an explosive reaction. That is the reason we preferably don't do any fluorination. Now even if you wanted to know, I want to do fluorination, you can do it by diluting fluorine by an electrochemical process, but that is a very tedious and costly process. So if a person is really interested to do fluorination, irrespective of whatever might happen, we can't take risk of explosive reaction, so they can deal with fluorine and diluting it. But even though that process exists, we don't usually prefer to do fluorination, looking at the effects it might cause, because it's an explosive, we don't want any explosion. So fluorination we usually don't prefer. Okay, clear? Because it's an explosive reaction, it is a highly exothermic reaction. The reason fluorine being highly reactive. What is the reason here? Fluorine is highly reactive. Now let us talk about bromination. Okay, let us talk about not bromination. Bromination is similar to chlorination, the process and mechanism and everything. Now when you come to iodination process, what is problem with iodination? Fluorination we understood, because fluorine is highly reactive. Okay, because fluorine is highly reactive, it is becoming explosive, so it is understandable why are we not preferring that reaction. But when it comes to iodination, if you see the iodination reaction, the main problem here is, the first thing is iodine is very less reactive. That is a major problem for us. First of all, it is less reactive is a very major problem. So the reaction happening, only the probability is very less. First, suppose if the reaction is happening also. First problem I already discussed. Okay, by chance, we didn't say it is unreactive, right? We told it reacts, but the reaction rate is less. Now imagining that it reacts also, because the rate of reaction is less but not nil. When it reacts, what do you get here? You get CH3I plus HA. But the main problem of this reaction is, this reaction goes reversible. Okay, this reaction is a reversible reaction. This reaction is a reversible reaction. Now if you people are thinking, okay, if it is reversible, then it is a problem, because you will get CH3I plus HI, but they immediately they immediately go back and again give methane plus iodine. So what is the point of doing this? Okay, it mostly prefers to go in a reversible direction. Okay, but there is a solution for every problem. Okay, now if you are thinking, first let us see why it is mostly a reversible reaction. We can't just say it is a reversible reaction and go forward. Let's try to understand why this reaction mostly goes reversible. Because the HI which is there here is a strong reducing agent. Okay, it is a strong reducing agent. When it is a strong reducing agent, it will oxidize itself and reduce others. Now when HI oxidizes itself, what it will become? Oxidation is removal of hydrogen also. Okay, so it will become I2. Okay, so it will act as a strong reducing agent and it will become I2. Now if you want to solve this problem, what should I do? If I want to solve this problem, what should I do? I should stop HI from interfering, from going backward, and interfering with the reversible reaction. So I will try to do something with the HI. For this process, what we will do is, we will use strong oxidizing agents, like HiO4, the periodic acid. It is a very strong oxidizing agent. Okay, you can also use mercuric oxide also, or HgO. Okay, now what happens is, because they are strong oxidizing agents, now as soon as the HI is produced in the reaction, it is a strong reducing agent, it will try to become I2. Now before it reverses the process and goes reverse, we will treat HI with the strong oxidizing agent HiO4. Now if you see here, HI plus HiO4, they both will react with each other, giving iodine plus water. Okay, giving iodine plus water. So we will isolate it separately and immediately oxidize into I2. Okay, and immediately oxidize into I2. Okay, now as soon as HI is produced, you are immediately using a strong oxidizing agent and converting into I2. Now because HI has already got converted into I2, now it will not go reverse. Okay, because we have done something with HI, we did it. Okay, we have treated it with strong oxidizing agent. HI has undergone what? Oxidation to give I2. So this HI going in a backward direction, we have hindered that process by treating it and stopping it there by treating it with a strong oxidizing agent. Now this is how iodination, it is a very slow process, but even if it is taking place, it is a reversible reaction. So that to avoid the reversibility of the reaction, why is it going reversible? First of all, because HI is a strong reducing agent. To avoid this process, we can treat HI with a strong oxidizing agent so that it gets converted to I2 and the reversible reaction can be hindered. Okay, so this is how the different halogens show their reactivity towards free radical halogenation reactions. Okay, so these are the points. Hope you understood all the points. Let us see two questions to understand this concept better. Okay, identify all the possible monochlorostructural isomers expected to be formed in free radical monochlorination. So I have to do free radical monochlorination of this compound. Okay, so let me write this compound, expand and write it CH2, CH3. I have two methyl groups on this carbon, so CH3, CH. So this is my compound. For this, what should I do? I should be doing monochlorination for this. I can't do dichlorination, I have to do monochlorination. And see how many possible monochlorostructural isomers can I get. Okay, now here you can see how many types of hydrogens are there, those many types of monochlorinations I can do. Means, okay, I can do monochlorination by substituting this hydrogen. So this is my one type. Okay, I can do monochlorination by substituting hydrogen of this carbon, because it is of different type, I get a different type of product. Okay, I can do monochlorination by substituting this hydrogen, because this hydrogen is in a different environment. Okay, now if you see these two methyls are in the same environment, because these two methyls are attached to the carbon having one hydrogen. Okay, whereas this methyl was attached to the carbon having 2 hydrogens. So this methyl and these 2 methyls are in a different environment. Okay, so but these 2 methyls, if you see, they are attached to a same type of carbon atom or the same carbon atom. Okay, so these 2 methyls, if I do monochlorination of any of these 2 methyls, I will get the same product. I'll get the same product. So I can do one more type of monochlorination here, A, B, C, D. Okay, so I have 4 different types of, okay, 4 different, or I will frame it this way. I have hydrogens, okay, 4 hydrogens in different environments. This is in one environment, this is in one environment, this is attached to this carbon, so all the hydrogens are in a similar environment. These 2 hydrogens are attached to on both the sides with this carbon atoms, so these 2 hydrogens are in a similar environment. This hydrogen is in an environment where it is surrounded by 3 carbon atoms. These 2 hydrogens of these 2 carbons are in a similar environment. So how many different environment carbons I have here? 4 different environments. So individually I can do monochlorination. Now let me do monochlorination of this. Okay, this hydrogen. So what do I get then? For A I will do. Okay, for A, for this I do. What do I get here? CH, CH3, CH3, CH2, CH2, Cl. Okay, so this is my one compound. If I do for this hydrogen, what will I get? CH, CH3, CH3, CH, Cl, CH2. Okay, sorry, I'm writing an extra carbon, I guess. Yeah, CH3. Okay, this is one compound. Here I did the monochlorination of this hydrogen. Okay, now I can do monochlorination of this hydrogen. What do I get here? CH3, CH3, Cl, okay, CH2, CH3. I did monochlorination of this hydrogen. Now I can do monochlorination of either of this hydrogen because they are in the same environment. So what do I get here? CH, CH2Cl, CH3. Okay, if you want, you can try chlorinating this and write the name. You will get the same name. Try chlorinating this, not this carbon, and see the name. You will get the same name. So I'm not writing one more structure by chlorinating hydrogens of this carbon because they are in the same environment. If you want, you can try writing it. You will get the same name as you get for this product. Okay, now if you see here, I got how many structures here? I got 1, 2, 3, 4 structures, 4 because I have 4 different hydrogen environments. Okay, now all of them are isomers. Yes, all of them are isomers here. Okay, all of them are isomers here. Okay, if you see, they have the same molecular formula but different structural arrangement. So all of them are isomers of, okay, all of them are isomers. I got 4 monochloro structural isomers. So how many I got? 4 monochloro structural isomers I got here. I got 4 monochloro structural isomers. These are my 4 monochloro structural isomers. Now you people are very good in naming, so you can try naming. I'll name for the first one. You try naming the others. So here I'll number from this side because I have substituent here. So I'll prefer nomenclature. I taught you in the second session only. If you want, go back and check it. Okay, I'll do it here. 3, 4. Okay, so what will be the name here? Okay, 1 chloro. Okay, 1 chloro, 3 methyl butane, because my main chain has 4 carbon atoms and my first what should I write? First I should write the substituent. Okay, so what is my substituent here? Okay, I have chlorine as a substituent and methyl as a substituent. I'll go with the alphabetical order. So 1 chloro, 3 methyl butane. Okay, other names you can try because you people very well know the naming. I'll do for the 4th one. Okay, I'll do for the 4th one. Okay, here if I want to take the longest chain, this is my longest chain and this is also my longest chain. But I'll prefer taking this as my longest chain because this carbon has a substituent. So I'll write from here 1, 2, 3, 4. Okay, what will be the name here? Okay, what will be the name here? 1 chloro, 2 methyl. Okay, 1 chloro, 2 methyl butane. Okay, 1 chloro, 2 methyl, and the main chain has 4 carbon atoms. So 1 chloro, 2 methyl butane. Okay, you can try naming the second and third structures because I have already taught you how to name the structures. Now if you come to this question, you can check, you don't have any other possibility of getting one more monochlorostructural isomer of this. I told you if you do here also, again you will get the same thing. So I have only 4 possibilities because there are 4 different environment hydrogens for me. If you see this question, write structures of different dihalogen derivatives of propane. Here we are talking about the monohalogen derivatives. Now we are talking about the dihalogen derivatives of propane. Now if you see propane here, CH3, CH2, CH3, I have to do dihalogenation. Okay, here I have how many types of, okay, let us see how can we do. I have to do dihalogenation. So I will take 2 carbons and do the substitution here. Okay, I can do in one possible way is I can put 2 chlorine atoms on the same carbon, CH3, CH2. I can put 2 chlorine atoms on the same carbon. This is one way I can do. One more way I can do, I can put both the chlorine atoms on the secondary carbon. This is my primary carbon, this is my primary carbon, this is my secondary carbon. I can put both, I can substitute both the hydrogens on the secondary carbon with chlorine. So what will I get then? CH3, CCl, Cl, CH3. One more thing, what can I do? I can substitute one hydrogen from the primary carbon, one hydrogen from the secondary carbon. Then what will I get? CH3, CH, Cl, CH2, Cl. This is one possibility. What is the other possibility? I can substitute one hydrogen from this primary carbon, one hydrogen from this primary carbon with chlorine atoms. So I'll get CH2, Cl, CH2, CH2, Cl. Okay, there is no other possibility now. Okay, because if I put on this, it is again the same, right? If I substitute this, it is again the same. Okay. So if you are thinking, ma'am, substitute 2 hydrogens on this carbon and put chlorine, then again it will be the same structure. So how many possibilities I got here? 4 possibilities. You people can try naming these structures and you can take the naming of these structures as your homework, because we did nomenclature of all the possible haloalkanes in this session 2 only. If you want to go back and check the session and try the nomenclature of these 2 compounds and these 4 compounds. So here your answer is 4 monochlorostructural isomers. So here how many structures of different dihalogen derivatives of propane I will get here? I will get 4 different dihalogen derivatives of propane. So this was about the preparation of your haloalkanes from alkanes by free radical halogenation mechanism. We have started the preparation of haloalkanes from hydrocarbons. In hydrocarbons we did preparation of haloalkanes from alkenes, so still we have other hydrocarbons left. This is only one part of hydrocarbons. Okay, this is only one type of hydrocarbons, alkanes, from which today I have shown you how to prepare your haloalkanes. In the next class we will be seeing how can I prepare haloalkanes from your alkenes and alkynes. Hope you understood today's session, where I have shown you in very much detail with all the mechanisms how to do the halogenation of your alkanes so that you get haloalkanes. I did 2 questions for your better understanding. Hope you loved today's session and you understood today's session. Any suggestion and comments, please put in the comment box. Till I meet you in the next class with the preparation of haloalkanes from alkenes, it is bye-bye.